So we're ready for the last talk of the day, which is going to be by Guido Boccali, and the title of the talk is Normalization for lax-idempotent sketches. Guido, tell
Oh,
us.
thank you. Well, this will be a very boring talk because even though it's supposed to be about two-dimensional logic, most of it will be about one-dimensional logic, and I will say many things that you already know. Not only that, I will do that twice, because the first time I will need to give some motivations, and the second time I will just look at the actual one-dimensional proof that we wish to categorify, and only then I will start talking about new results. So, without further ado, let me start. Well, as you know, in the 60s, Lovier introduced functorial semantics, and the fundamental idea is that theories are categories where objects are sorts, morphisms are definable functions, and commutative diagrams are provable equations. Models of those are functors into set, where for each sort we get a set, for each definable function we get an actual function, and provable equation must hold in virtual functoriality. So, oh, sorry. Okay. Okay. But this is quite a scarce notion of logic because even for purely equational logic, we need at least products of sorts. For example, we want a terminal object to talk about base points or binary products to talk about binary operations. And indeed, each logic requires a universal construction of some sort. For example, if we want to speak about predicates, we need monomorphisms, so some kind of pullback conditions. Conjunction of those are pullbacks. The existential quantifier amounts to having certain pullback stable equalizers, and we can go on and up until if you want, if we wish to have dependent product of sorts, we need to ask our category to be locally Cartesian closed. But I'm sure many of you have seen the like giant tables on the MLab about that. Um, but so we seem to have a pattern. We have categories of some sort, which are ranging to a two category. And set is, well, most of the times one of those L categories of kind L. And if we ohm into set, we get a functor giving models of our theories and we give it like a proper category of models of our theory. So a very natural question, that a very old question is, can we have a general framework for that? Many answers has been given in history. Via KZ doctrines, the general theory of sketches, the theory of topoi, clubs, props, and so on and so forth. But like in the 90s, John Power had introduced this idea that categories of a certain shape, like with a certain structure or with certain properties, are actually models of a two-dimensional theory, just like structure sets are models of a one-dimensional theory. So the idea is that to study categorical logic, we need to study essentially algebraic two-categorical logic. This notion of two-dimensional logic has gained interest in recent years. Just to name a few works in this community or orbiting this community, we have Diliberti and Osmond, the work of Diliberti and Osmond, the work of Archer, Burke and Co., and the forthcoming Gambino and Tandats, which has been presented in this seminar. Um, so the among these works, like the only work that I'm sure that like has this precise motivation of studying categorical logic is the first one, but the examples covered by the others indeed somewhat go in this at least partially in this direction. So um, now let me go back to again to one categorical logic and just see what we want to do in the present work. Essentially, algebraic theories correspond to Lex categories, sorry. But in practice, it's pretty hard to specify an entire category with finite limits. For example, if you want the theory of monoids, you have to specify the whole category of simplices. Indeed, yeah, to specify a theory, we only want to specify certain terms and certain equations, and then we want the logic to do the work. So, to this end, we use sketches. A finite limit sketch is a category C with specified finite cones, um, whose intended interpretation is to be actual limits. For example, if I have a little square and two triangles with two intended projections, a model, and I declare this to be a specified cone, I want a model to be to turn the square into a product of the interpretation of the triangle and the two maps into projections. So the natural question, the very first question that one comes up with is this really a presentation for finite limit theories? And if you look a little bit closer to this question, you're just asking, is there a biadjunction between the two categories of sketches and the two categories of lex categories, which is actually a reflection, that leaves over the model's functor of, of the two categories? And if you ask a little bit closer again, from a logical point of view, if the unit of this biadjunction is faithful and conservative, this is a normalization result. But to prove this result, one uses Gabriel-Ulmer duality, which is this notorious equivalence between lex categories and finitely representable categories, well, the opposite of finitely representable categories, given by taking models and extracting a theory back. So, if we want to prove our result, we only need to prove that actually the two-functor mode factors through presentable categories, and that its right adjoint is this composition. We take a presentable category, we extract the theory, and then we include back into sketches. And again, from a logical point of view, if the unit of this adjunction is faithful and conservative, this is a completeness theorem. So the main ingredient is to actually show that the category of models of a sketch is presentable. So what does it mean? That if I have a model sketch whose base category is C, I want to show that it's accessibly reflective into the category of co-perceives of over C. So I want to show that there is a like okay, you know what I mean. Um, to to show this, one employs the small object argument, which gives us this equivalence between idempotent monads on the perceived category and orthogonality classes of inside that. And with a small refinement, one gets that finitary idempotent monads are exactly the same as finitary orthogonality classes, which just means that the the objects are compact. The objects in the class of maps are compact. How does that work? Well, you take a specified cone with diagram C and tip, well, diagram D and tip C. Um, you you look at co-perceives, and you have well, Yoneda of the tip and Yoneda of the diagram. You can calculate the colimit of the Yoneda of the diagram, and the cone actually becomes a co-cone. So we have a canonical map from the colimit to the tip. Now, asking for a general co-perceive to be orthogonal to this map means just by a simple Yoneda computation that the co-perceive X is like maps C into the limit of D. Indeed, if you follow this diagram, it is pretty clear that if one of the vertical lines is an isomorphism, then the other is so. So the idea is asking for orthogonal for well to say that to declare that models are the orthogonal objects with respect to this class of maps. So let's try to raise dimension. We have a theory of bi-accessibility and bi-presentability. In many forms, we chose the one presented in Diliberti and Osmond. In that work, a Gabriel Ulmer duality is developed, so we are fine. For a small object argument, we have a small object argument developed in Diliberti, Lobby, and Sosa, which is like quite what we were expecting, because indeed, there we are not, they are not considering genuine orthogonality, but can-injectivity, where genuine orthogonality means that for every map, well, to be orthogonal in the bottom diagram, to be orthogonal to the horizontal map just means that we have an isomorphism of home sets. Like you see, maps from X to Y correspond exactly to maps from X to Z. For weak can injectivity, we simply ask that for each map from X to Z, we have a left or right can extension, so that actually we get an adjunction of home categories. So the theorem they prove is that can injectivity classes correspond exactly to KZ monad, and a KZ monad is a lax-idempotent monad, where an idempotent monad is characterized by the fact that being an algebra is just being an inverse to the unit, and so yeah, being an inverse to the unit. For a KZ monad, being an algebra means just being yeah, a left joint to the unit. So in both cases, an algebra structure is really just a property. Well, our first little trick is to categorize a lemma in the classic Adam Rosicki's book, and to show that with can injectivity we can also play the game of essential orthogonality, and we also can refine the result by saying that bifinary classes of maps are bifinary KZ monads, induced bifinary KZ monads. So we now can ask if this lax idempotency is a feature or a bug. Given our intended examples, we want to be able to interpret a map, like from a little circle to little square, just as the diagonal map of a model into the power of the model with a certain category J. So that asking for and asking that to have a left or right adjoint, so that we can compute limits and colimits of shape J. So this is like something that we actually want. And so we can define co-KZ sketch, which is a two-category K, together with a set delta of weighted bicones, and a set sigma of maps that we want to turn into left or right adjoint, depending on the variancy of the sketch. Our theorem is then just to show that there is a tri-reflection between the tri-category of co-KZ sketches and the tri-category of bipresentable categories. Just in the same way as before, we extract the, well, the left adjoint is taking models, and the right adjoint is extracting by Lex theory and then including into sketches. And we also show that the unit is locally fully faithful, that is exactly the right categorification of the requirement that before was being faithful and conservative, so that we are good. So as a corollary, we have the expected corollary, so that we have a reflection of bilex categories, two categories, sorry, into co-KZ sketches that leaves over the model's trifunctors, whose unit is, again, of course, locally fully faithful. We can capture known examples. Of course, we can sketch lex categories. We can sketch for a specified class phi of shapes. We can sketch phi complete categories. And then, again, given two sketches, it's pretty easy to sketch a tensor product of those, though which we do not prove that like this constitute trimonoidal structure on the tri-category of sketches, because that would be like a pain of coherences. But this is still pretty useful to have, because if we tensor the lax categories with the phi-complete ones, we get the phi-exact categories, so the ones in which the phi colimits commute with finite limits, which are exactly the ones that one would want in categorical logic. And then we have new examples. Indeed, um, a couple of years ago, Taiichi Uemura introduced formal type theory to code flavors of type theories, such as dependent type theory with sigma types, dependent type theory with pi types, with identity types, and so on, and all kinds of type construction. And it also includes cubical type theory. And then, for each such a gadget, he can produce what is called a category with representable maps, which is quite like the display map categories that Matteo was talking about before, but with a quite different flavor. Each category with representable maps has a two category of models, which is morally the two category with families or natural models representing well with the appropriate structure. But what we show is that indeed a category with representable map is best understood as a Cauchy sketch. And yeah, so we can sketch those category of models, the category of models of a CWR in a pretty easy way, and show the theorem that like all those two categories of models are bipresentable. And so I've been very short because I was speaking too fastly, sorry. Uh, but I'm done.
Okay, thank you very much, Guido. We thank the speaker silently. Actually, now we have some reactions finally. Now people can see reactions. When a couple of years ago, this was not a feature. Uh, so let's see if someone wants to make a couple of questions. The floor is open. Ling Yuan seems to have a question.
Yeah. Thanks for the very interesting talk. I was wondering, can you sketch whole sets via toSketch? You can.
Yeah.
So in particular, when you take the tensor, say of I don't know, some phi colimits, some limits with the posets, do you get the intended thing? Or
Yeah, yeah, precisely. If you can sketch like distributive lattices, for example, in a pretty easy way,
uh-huh.
because you can sketch exactly because you sketch posets and then you tensor with the yeah.
But this is like the part of the thing that I kind of don't understand, because say when you sketch finite co-products,
Hmm.
for instance, this will give you like extensive categories, I guess.
Yeah,
But when you tensor with the posets, like for
yeah.
distributive lattices, the co-products are not disjoint, right? So like how does this tensor work? I'm
Um, well,
a bit
this is
confused.
a technical question I didn't think about, but like, well, I can explain the tensoring. It's pretty easy, but we can think together about it. Um, I would guess that you ask for, well, if you want if I had to sketch distributed lattices, I would ask for finite colimits, finite limits. I tensor them, and then I tensor the resulting theory, which with posets, the theory for posets, so that I get distributive lattices. Um, yeah, of course, finite limits reduce to finite products, but I don't know really.
Okay, but thanks. This is quite interesting.
I can check, of course, and we can talk about it.
Okay.
Do we have other questions from the audience? Maybe I have a comment on the last question. But Lincoln, what's the problem? I mean, in the definition of the extensive categories, it's not really like in the axioms the coproducts have to be disjoints. They just happen to be. And then, of course, when you ask the things to be opposite, then they will crash. But that's their problem, not yours. It's not like there is something absurd there, right?
No, I'm just saying the tensoring with, say, like extensive. You can perfectly sketch like extensive categories, but when you tensor this with a poset, it should give you a trivial thing. Because this is what I'm asking, maybe.
Okay, so now I understand better.
I should think about it. I don't have a strong opinion, but I was confused by the question. I think we can still ask a couple of questions if there are. We don't have other questions, then thank you very much, Guido. This was a very interesting talk, and see you in no, sorry. We thank the speaker one last time. Thank you.
Thank you.
And then I think see everyone in September. Is it so? I think so, right?
Yes, in the morning.
In the morning, that's true, because it's going to be a bit of a special session with a lot of invited speakers from other continents. So see you everyone in September, and thank you for coming.